Good afternoon, everyone. My name is Chen, and now I'm working in the Seoul National University OEQ lab as a postdoctoral researcher. And it's my pleasure to give you a talk about my research topic is about improving the color accuracy in holographic display. Holographic display is regarded as a next generation display technique since it has the ability in reproducing photorealistic 3D images and deliver an immersive virtual experience to the viewer. And recently, the holographic display gets more and more attention over the world. If we search in some information on the internet, we can source some very excellent work. For example, recently published on Nature, they using the inverse design and the neural network realized a very high quality AR display. And also there is a team from Stanford University. They through the time multiplexing and the neural network realized a very high quality holographic display. In their result, they have very natural defocus blur. And also from their team from the Seoul National University, they demonstrate the holographic parallax can improve in the 3D perceptual realism. And also there is a paper published in 2020 in SIGGRAPH. They proposed there exists a mismatch issue between the holography experiment and the simulation, and they proposed the neural network to parameterize the optical propagation mode. And one of the big advantage of the holographic display is that it can realize the true 3D display. And here is a compare between the traditional 3D display and the holographic display. Assuming we have a 3D scene here, if we display the scene on the traditional VR display panel, actually our eye is focused on the screen with the distance dy, but the real depth of the scene might be different from the D1, maybe from the D2. So this mismatch is called the divergence accommodation conflict issue. Because of this mismatch, we may feel like uncomfortable after using these kind of VR devices for hours. But for the hologram display, the 3D images can be reconstructed in the free space, so our eye can focus at anywhere, so there is no VAC issues. These characteristics render the hologram display promising in the AR and the VR application. And to realize more realistic 3D display, we need to consider a lot of factors. For example, to make our eye, when our eye focus at the different depths of the object, we can see this kind of the focus blur effect. And another thing is the occlusion. If the back object is blocked by the front object, we can just only see part of the back object. And another thing is called the parallax. If we see the 3D object from a different view, we can see the different part of the object. And another thing is the lighting, shadow, and the reflections to make to render the object more realistic, also including the color and the textures. So the previous three features is to make the 3D images and the back of the rest of them is to make the high quality 3D images. This is like a rendering process. So in hologram display, there exist a lot of limitations. For example, for now, the main limitations including the form factor and the mismatching issue between the simulation and the experiment. Like currently, the kernel devices of the hologram display is called the special light modulator and the laser, and their size is over too big. It's really hard to make a lightweight of them. So it is hard to integrate it to the current AR and VR systems. Another thing is the mismatching issue between the simulation and the experiment. This kind of mismatching issue can introduce the spectral noise and also the color accuracies. And as a display technique, holographic display also need to guarantee the 3D image quality. However, the quality is heavily limited by the imperfect optical systems. like in our holographic display systems, the lens is not perfect, and there exist some like aberrations and some like scratches and dust on the lens, and the also the light modulation devices is also not perfect. There exists some like a nonlinearity characteristic, and also the light source is also have some like problems, like for example, like the color uniformity. So this kind of devices can heavily degrade the holographic image quality. So if we do not do the optimization for the holographic display, we cannot like to deliver this kind of quality image to the users. It is not suitable for commercial uses, so we need to improve it. Except the noise, the imperfect optic system can also affect the color accuracy of the holographic display. The color like may deviate from our expected color, which can affect the user's watching experience. So in this report, my research is mainly focused on how to make the holographic image's color more close to its original color. And in the 2020, there is a team from the Stanford. They consider the system's imperfections into holographic display and to solving the like imperfection. I mean, to mitigate the gap between the simulation and the experiment. So now I'm gonna briefly introduce the principle of their method. So assuming we have a laser, we have a hologram in here. So firstly, we upload this hologram into our holograph display system, and the laser generate light. After the light through the holograph display system and modulated by the special light modulator, our camera, we use a camera to capture the reconstructed holographic image, and we get the captured image. And at the same time, there is a forward propagation in the simulation. We can get the simulated image. So if we replace the captured image, we replace the simulated reconstructed image with the captured image, we can get the optical captured feedback. So that is more natural. So if we compare it with the pocket image, we can get a loss function, and we can using this loss function to update our hologram and repeat this process. And finally, we can get the holographic image. And you can see for this kind of optimization process, things if the light source is calibrated well, then it's okay. But if the light source is not calibrated well, then the CITR method is hard to accurately reproducing the color, because the ability of holography in color control is limited. So if the color source is shifted, then the holography reconstructed color will also shifted. So we need to, usually what we did is manually adjusting the laser's RGB ratio to get a proper color balance. But this kind of optimization method is like like effective feedback to realize the accurate color reduction. So to solving this issue, we proposing integrate the laser and the camera in the optimization process. This is called the laser camera in the loop optimization. For the CITR method, when our camera captures the image, the captured image will be replaced to the simulated image as shown in the left figure, and the loss will be used to upgrade the face-only hologram. But for our laser camera in the loop optimization process, the calculate loss function will not only used to the upgrade the hologram, but also the S factors. The S factors will be used to the dynamically update the laser's output color. So And in the loss function calculation process, we didn't introduce any like S factors in this process, and we just need to the absolute intensity instead of the relative intensities. And here is the overall process of our laser camera in the loop optimization. And we still from this we still begin from the hologram. We upload this hologram to holographic display systems, and the laser generates light from the generates light, and through the holographic display system, the camera can capture the image. And at the same time, we also have the simulation process. We will replace the simulated image with the captured image, and calculate the loss with the target image. And then we propagate this process to update the hologram and the laser's output color, so that the laser's color is when we repeating this process, the laser's color is gradually corrected, and so that we can realize the more accurate color reproduction. So, and in our simulation process, in order to simulate the imperfect light optical system, we manually introduce some like intensity noise. We firstly prepare a white hologram and upload it to our systems, and we using our camera to capture the reconstructed results, and we're using the initial intensity variation to simulate the imperfect light source in our simulation. And this is our simulation parameters. And here are the simulation results, and you can see for the stochastic gradient descent method, you can see there. Since there is no physical feedback, so the image quality is quite bad, and the color accuracy is also not corrected well. For the CITL method, it introduced the camera in the optimization process, so the systems like the noise can be suppressed well, but since it didn't have the ability into dynamically adjusting the color, so the color is not satisfied enough. And with our method, you can see the color, and both color and the image quality and noise is suppressed well. It shows the best image quality compared with other methods. To demonstrate the effectiveness of our method, we also built the optical experimental result. And the left one is our optical system setup, which consists of the laser, illumination lens, polarizer, beam splitter, SM, and the 4F system. This is to filter the high order light, and also the sensor is used to capture the image. And we also using a linear multi-stage for 3D supervision. And here is some like experimentally captured 2D images. You can see it is similar to the simulation result. The SGD it shows the worst image quality. And the CITL method, the further noise is suppressed well, while the color accuracy is not satisfied enough. For our method, both noise and color accuracy is better than the previous method. We also using to describe the color accuracy improvement. We also projected the each pixels of the image into the CIE color space, and we can see the results. And the red one shows the color distribution of the target image, and the blue one shows the color distribution of these different methods. And you can see for the SGD one, you can see their color is shifting a lot, which means their color accuracy is quite bad. We can for the CITL method, you can see the color is kind of overlapped, but we can still see this kind of clean color shift issues. which means the color is still not satisfied enough. And for our method, we can see most of the colors overlap each other, which means the color accuracy is higher than, is better than others. And here we also did the 3D reconstructions. And figure A is when the camera focused on the flowers, and the figure B is when the camera focused on the butterflies we can see. And you can see for the SGD method, the image quality is quite bad. And for the CITM method, the noise is improved. And for our method, you can see it shows the best image quality and the color accuracy. And also to test the robustness of our method, we did simulation and the optical experiment result. And this is from the different laser initial conditions. You can see we did 3 tests, like from the red initial condition, green color initial condition, and the blue color initial condition. And when the optimization process going on, you can see all of them can like converge to a good color accuracy condition. The color can be corrected well with our method. And this is in the optical experimental results. And you can see the similar trend. No matter how we initial how the color is initiated, they can all like realize the good color accuracy. And here is a compare with when the S factors and the different illumination condition. We can see it is quite similar to the voltage change in the optical experiment. And here is a sweep compare between the different among different methods. We can see the difference between them. We also did the optical experiment for different images to test the robustness of our method. And you can see, compare with the CITR method, our method's PS9 improved 4.35 dB on average, and the delta E reduced 37.3% on average, which means our method's quality and the color accuracy is the best compared with the other methods. And finally, thank you very much for your attention.